to talk about today. Probably won't be able to finish this, but at least I think I will be able to get to the point that how to do the sequential synthesis if you want to. Okay, so we talked about in class that sequential synthesis makes sense because the sequential conditional multiplied together will give you a good approximation to the joint, all that. So that all makes sense. But now we're talking about combining rules and then doing demonstration for a fully synthetic data set. So I'm trying to, again, using the CE sample and then trying to share with you how to do fully synthetic data in the first place and then talk about the combining rules. The combining rules, okay, again, not very different from before. We still have our Q and V, so I still have my typo here with S squared divided by V. Okay, so those are the same. Okay, you have your capital Q, that's the univariate estimate. You have Q and V, those are point estimate and variance estimate of Q from the confidential data. And then you know that the QI and VI that we calculated are from each synthetic data. Okay, so same procedure. Equations 6, 7, 8 are exactly the same as before. That you're getting the Q bar M, BM, and V bar M. Okay. The difference here, as you can see here, and as you read through the paper or the chapters as well, is that for full synthesis, you also have different sources of a uncertainty, but there is some more subtlety behind that. We have to use a new type of variance estimate, which gets a tricky caveat here as well. So equation 9 is what we use, and you might be wondering, why do we do minus instead of plus if we do have different sources and all that? So it's not an easy question to answer, and but overall, just I guess have faith now that this will be the right way to quantify the variability of Q. With Q bar M when you have fully synthetic data. But there is a caveat here because when you have something minus something, both of them are non-negative, it's possible that the TF, which is the full synthesis, the T, the variance estimate of Q bar M for the full synthesis, it's possible that it becomes negative. But we cannot have negative variance, right? So people have proposed other non-negative variance estimator. So I covered this one, equation 10. So pretty much this adjusted or alternative variance estimate is trying to take the max between the two, which, well, in our case, if you're going to have a negative TF, this part going to be 0, okay, because you're taking the max between those two. And then so this second term here is really trying to capture the variability still if your first term is 0, because there will be some variability. So just bear with me. Delta, this thing, is 1 if you have a negative. So that's why that term going to take into effect. Otherwise, if that term is 0 when TF is positive, then it's just TF. You don't need to deal with this. So this thing, a bit complicated to explain, but for us, I think let's just take it for granted in the sense that the N syn, so you see here, I'm copying that sentence from the chapter, and you might be confused, oh, what does it mean to have the number of observations? The reason it's sampled from the synthetic population. So short story is, when fully synthetic data was first proposed, it's not doing what we are going to do. So you will see that soon when I'm trying to synthesize both log expenditure and log income, I'm doing it sequentially, okay? And since I replace everything, I'm saying that I'm doing fully synthetic data, okay? So it is more and more doing, it is more and more commonly done now in this way, but when it was first proposed, it's not supposed to be done like that. What they mean, especially the synthetic population, what they were doing in the first place when the method was proposed, I think early 1990s, what they're doing is that you synthesize a synthetic population first. So you have a sample at hand. Okay, I want to do fully synthetic data. So instead of replacing every attribute or every variable through a model, what the original methodology was, we have to generate a synthetic population that is much larger than the sample that we have. And then we take random samples from the population, from the synthetic population, to be our fully synthetic data. Okay, so that's how the original method was. So you can think about this as our sample, right? This is original confidential. And let's just say we created a much larger synthetic population, okay? And then the fully synthetic data set is coming from this. Okay, so that's just how the methodology was proposed in the first place, and that's how those like binary rules was developed. So that's why you have this n seen, which in our case just going to be n. Okay, because n seen, based on their definition, is the number of observations in the release data as a sample from the synthetic population, because we are doing exactly the same size as the original data set, like we're doing fully synthetic data for it. So n seen will just be n in our application. So it's just going to be 1. Okay. So once you have that in place, the TF star, the adjusted value, will just become V bar n. Okay. So short story is that if TF unfortunately becomes negative, we're just going to use V bar n as the variance. So we can just take that for granted for now. And like I said, happy to, I will be uploading some references for you to take a look. And if you're curious about it, but in practice, that's what we do. All right, and then you also have your VF, this is degrees of freedom, and then you're also gonna have your confidence interval for Q by doing this central limit theorem type of work. Okay, everything flows on, flows smoothly. I should probably update this part just to be TF star. Okay, because we do have possibility that you will have to update it using the adjusted version. Okay. All right, so I think all of this is okay. So let me spend the last 5-ish minutes just to talk about how you can do things sequentially. Okay, so we talked about conceptually how you can do it, but in practice, you would take some practice and make sure that we're doing the right thing. So now we have to do synthetic data, fully synthetic data with CE. So that means we not only have to synthesize log income given log expenditure, we also have to synthesize log expenditure. Okay, and a natural way to do it, like we said before, is going to do it sequentially. Okay, and since we are trying to synthesize log income given log expenditure, so maybe the sequence should be we do log expenditure first, and then log income given log expenditure. Okay, but you can do the other way around if you want. But what I'm going to do here is that the first step is synthesize log expenditure. Since it's a univariate numerical variable, I'm just going to develop a simple normal synthesis model for it. And once I have that, I can synthesize my log income from the previously developed simple linear regression synthesis. Okay, so that's why I said step 2 is readily available from the previous example, but we have to develop step 1 here. Okay. So step 1 is from a normal synthesis model, so nothing fancy. Everybody remembers this. I hope that you can write a simple JAX. Well, to be fair, I think back then in 347, we didn't use JAX for this kind of model. Like we're writing our own, not writing, because this is analytically available, because it's a conjugate prior that I'm using. So you are able to, write the analytic solution, but let's just use JAX all the way through. So this is, you can see, a simple, normal synthesis model, right? I have my mu and sigma. These are inverse sigma 2, those are inverse sigma squared. Both of these are parameters, right? I put priors on them, so then I will be able to get posterior draws for them, and then I can do posterior predictive. Okay, so that's the same thing as before. So nothing fancy here. I'm using weakly informative prior, and everything follows. Okay, but note that here we're working with log expenditure, so make sure that you pass the right data to the model when you're doing the estimation. Okay. The reason why, so here you might be wondering, because the other one, the ones that we did before, we have to think a lot. So this is, again, it's always important to check your MCMC diagnostics to make sure that you're thinking enough. I chose one because once I ran this first, I looked at the MCMC diagnostics, the autocorrelation was totally fine, so I used one. Okay, but the other one, the earlier one that we used, we need to do it for 50, I think, and that's why it's taking longer. Last point here, to do the posterior predictive distribution, now we know You can save your posterior into like MCMC object, so we can extract those columns. So what I do here, so because the normal model is yi is normal, mu, and sigma, right? We have parameter draws for this, parameter draws for this. So naturally, you just do R norm, n is the number of observations you have, and then you get the mu and sigma from the columns of your data frame. And then that's it. Okay, so that part is fine, I think. The key here is how to do it sequentially. Okay, so I'm just gonna walk you through this. So okay, so first of all, I wrote, let's see. Yeah, so this is the function that we wrote for synthesize the log expenditure from a simple, like from a normal model. Okay, so I just to differentiate things, I also renamed the synthesis model, I mean the function that I wrote, just to differentiate that this one is to synthesize the log income given the log expenditure. Okay, so that's why you see, I mean, because earlier I think I only just have it synthesized. There's no extra name on this. So look at the flow here. We get the n, number of observations, fine. Number of synthetic data is fine. We also create an entry list to save that. That's fine as well. So let's look at the procedure. We set seed, that's all fine. So first of all, we did what? We synthesize the log expenditure. So I name it as synthetic underscore log exp. So we synthesize it from the function that I just wrote, right? And I'm using a particular iteration, I'm setting a particular seed, I need n of them. I put it as a vector, so later this is going to be a vector. Okay. And then the second step, I get a new seed just to differentiate from before. And notice the change. I'm using this function. This is the function that if I have a, if I have log expenditure, I can use that to synthesize log income. Okay. But notice here, this is the key. Is this thing, right? So when we mean sequential synthesis, we estimate model on the original data, that's totally fine, that's what we did, right? But when you are generating data, generating synthetic data in a sequential manner, I'm generating my log expenditure first, because that's my first step, right? So now I have my synthetic log expenditure, so I should use them to synthesize my log income. Okay, so if you remember what was here before, if we're only doing the partial synthesis, it was what, like CE data, whatever, and then $, like log expenditure, whatever that is. So we're using the original data, which is fine because back then it was partial synthesis, right? We should use the original data, okay? But now when you're doing a sequential manner, and this is true for any other models you're gonna do, the order you have to, you can develop your model whatever like order you want. You can estimate. So in here, what do I have? I have two MCMCs, right? I have a bunch for this, and then I have another one for this. Okay, I already have my draws there. Those draws are estimated on the original data, so they're just sitting there waiting for me to be used. Okay, and then when I'm doing this sequentially for full synthesis, in this case, is that I have to go into my first set of MCMC to get my synthetic log expenditure, and I have them. So they should be the ones that I'm going to use when I'm synthesizing the other variable, because that's how I specify my order. Okay, so just to be fair, those MCMC draws, they're already estimated because they're estimated on the real data. Okay, so you don't need to re-estimate it. Even now you have new synthetic value of log expenditure. You can use them, and you use them directly from what you just did before. Okay, so I think this, and then at the end, you name it and then put it into the list and all that. Okay, so I just want to, it's good that we get to cover this because I think for next week, well, we do have a lot to cover, I think, so I probably wouldn't assign too much more reading at this point, but think this through how you're going to do it in practice, like what you're doing for your project. And I think with this in mind, I think you're probably, I hope, in a better position to figure out like how to develop those synthesis models for your data. And then for some of you, I mean, I don't know, like Reese, for example, are you going to try to use the fancier model for the ordered categorical?
I tried, I didn't get it to work.
Okay, well, come to office hours tomorrow if you want. Yeah, so So I think I will give you the space and time to figure that out. So next time we're gonna finish up this. I mean, there are a few, yeah, like 20 more slides and stuff. I will talk a little bit about risks and stuff, and then hear from each of you or each team of your project to present what you have used, like what are the models you're gonna use, and then maybe some basic utility measures that you're able to like obtain from your synthetic data for your project. Okay. All right. So I'm gonna end here.